Okay, we are moving on to chapter 2. And chapter 2 is continuity and limits. So this first lesson, chapter 2, is 2.1, continuity. So let's take a look at some definitions. Okay, first, suppose function f is a function with domain D. Okay, and from real numbers, the domain goes range of real numbers to real numbers. Okay, the function f is continuous at some point A if two conditions. The point A, quotes there, is an open interval I contained, so we're calling this interval I, the A is an interval, we'll call that interval I, contained in domain D. So we're in an interval, so we're talking about an interval, right? Here's our interval from A to B, and we have some point, we'll call this C. Here's our interval, and that interval is open. And so within that interval is domain real number to real numbers. Okay, for each positive number epsilon, there is a positive number delta, such that our absolute value of the difference between our function and f of a is less than epsilon whenever x minus a is less than delta. So what does that mean? That means that, well, let's take, in order to look at that, we need to look at the graph. So here we have y-axis, x-axis. And we have some function that extends up like this. And back this up a little bit. And so we're saying here that we're saying that the function f can be this. This is our function f. Is within domain, so this is our domain, at A. So we'll make this point A here. And so with this point, if we go up to our function, we get a limit. And so what we're saying here is that with f of a, so what we're saying here is our absolute value of our function f of x minus f of a, so our limit would be the same thing as f of a, because that's our y value for a, right, is less than epsilon whenever x minus a is less than some number delta. Okay, so if we took the absolute values off, right, then we have here negative epsilon is less than f of x minus f of a, and that's less than positive epsilon, because with the absolute value, that's going to be, you can have epsilon as positive or negative. So if we apply plus f of a plus f of a plus f of A, we get f of A minus epsilon is less than f of x, which is less than f of A plus epsilon. Well, whenever we have x minus A is less than delta. So if we took that x absolute value of x minus A is less than delta, then we remove the absolute values, we get negative delta is less than x minus A, and that's less than positive delta. So if we applied plus A, and plus A, we get A minus delta is less than x, which is less than A plus delta. Well, what does all that mean? What we're saying here is that if we have as we're approaching A from the left, we're approaching A from the right, or from the right, then we're getting closer and closer and closer to our limit from either side. So if we can set a range, we're saying, okay, if we want epsilon would be from our limit to some number. So this would be f of A minus epsilon, and this would be f of A plus epsilon. So if we want to get within a certain range close to our limit, then what we're saying is if we set a delta, if we want an epsilon, then if we find a delta, we can find a delta that can guarantee getting within this window here of epsilon. So that, let's say this were f of A were, let's say 3. Okay, let's say f of A were 3. And let's say f of epsilon were 0.5. So this would be 3 plus 0.5 is 3.5. And so this would be 3 minus 0.5 would be 2.5. So we're saying we can get within 3.5 to 2.5 close to this limit if we can find a delta that can guarantee us getting as close to this limit as possible, like within 3.5 to 2.5. So this would be A minus delta and A plus delta. That's these numbers here, down here. So we're saying that if we have some x, okay, that's the difference between x and A, okay, some number x, that's the difference between x and A, it would be less than delta, we can guarantee being within this epsilon range. So this is delta, this is delta. All right, so what we're talking about here is getting within this box right here. We can get within this box, we can find some delta, if we can find some delta that can guarantee that we're going to get a certain closeness to our limit. So what we're going to do in our problems is we're going to say, all right, we want epsilon to be some number. Find a delta that can guarantee that we can get that close to our limit. Okay, so we're saying for each epsilon greater than 0, there's a number delta. So what we're saying here is for each, erase this, for each epsilon that's positive, right, or greater than 0, there exists, and this backwards looking E means there exists, there's an E in there, there exists a delta greater than 0, where the graph, where f, our function, remains within our domain of a minus delta to a plus delta. Okay, we're within that interval, within this interval. And so that we're saying that the verification of continuity requires that for every epsilon greater than 0, we exhibit a delta and show that our function lies within the approximate rectangle. So we're given an epsilon and we need to find a delta. If we can find that delta, then we have established continuity. And so that's what we're going to do in our next problems. And that's it for this video for now.